Okay, because it matters how I post it, right? Okay, so let's see. Am I sharing? Yeah, I'm sharing, and I'm recording for chapter 1. Okay, so I do have chapter 1 here, and so we'll start with chapter 1. Chapter 1 is essentially chapter 2 is the second chapter in the course because we do go over chapter E. Even though E is called essentials, we go over it. So this book is called Adam's First Approach, and the idea is we're going to study the elements, but we'll start from the smallest measurements or the smallest units, and then we'll build up from there. So we go from atoms to molecules slash compounds, from compounds to reactions, right? So you have reactions. That's kind of the general trend of how the book was written. We study atoms, the base of matter, and then we see how atoms combine to form molecules and compounds, and then we see how molecules and compounds react with each other in the context of a chemical reaction, okay? Ergo, the atoms first approach. Okay, so looking at the atoms, we're told that the view of the chemist is everything around them, right? So the chemist is looking at things around them and trying to answer this question: what are things made of? Made up of, okay? Let me see. Why is this page? Okay. Yeah. What are things made up of? Okay. And so we're told here matter, everything around us is classified as matter. Matter is composed of particles, and these particles are usually atoms. Okay, so we have matter being made up of particles, and we'll talk about the atoms later on. For right now, matter is also defined as anything around us that has mass and occupies space. So even if we can see it or we can't see it, whatever we're experiencing, as long as it fulfills the following criteria, it has mass. It can be a very small mass, but occupies space. We will call that object, that thing, that chemical matter. Okay? So chemistry is that discipline in science that seeks to understand everything around us that we call matter and the behavior, the property. Okay? So at some level, I feel like chemistry is the psychology and the sociology of elements. We're trying to figure out, we don't ask the elements, how do you feel? But if you look at the language later on, they use terms, human terms, terms that we understand. The element prefers, the element wants, the element goes after, like it has personal goals, right? Or should I say elemental goals? Anyway, our goal is to understand matter around us. When it comes to the composition of matter, matter, as I said earlier, is made up of particles. So particles make up matter. And at this level here, please notice when they talk about particles or particulate, that's talking about the level of atoms and molecules. So anytime you think about atoms and molecules, think about particles. So if they don't want to say atoms and molecules, they just say particles. That's the umbrella term that represents atoms and molecules. So atoms are the basic submicroscopic particles that constitute the fundamental building blocks of ordinary matter. In other words, just like you have one piece of Lego, right? And you can use all the Legos together or apart to build different objects and shapes and stuff like that. You can use individual atoms to eventually build up the macroscopic level of matter, what we can actually see and experience. So atoms are the building block of matter, and it says so right here, building block of matter. And then we're moving on to molecules. So if there's atoms, water molecules, and I told you guys this before, the difference between atoms and molecules, okay, is atoms tend to exist for the most part, mostly as individual units, the building block, okay? So you have that version of atoms, and you also have this version of atoms. The left version of atoms, you have individual units in the atoms. They call that monoatomic. So each unit of the atom a single atom. The right, not the right, but the version I drew on the right that also represents atoms, these are the kind of atoms when they're by themselves, they just can't exist by themselves and be stable. So they bind another atom to be stable when they're alone. When you see them in single form, they're usually diatomic. So these are called diatomic. And they're usually by themselves like that, diatomic in nature. Okay, di representing two. We also have triatomic, tetraatomic, all these other versions of atoms combined together, but at least you want to know these basic ones here. Okay, with the molecules, molecules in general represents any two atoms combined together. Well, you can have, well, it can be two or more. So minimum requirement to have a molecule is you have to have two or more atoms combined together. Okay, and they combine together in specific geometric arrangement. It took me a while as a student, especially middle school. I mean, you're a middle school teenager, right? And it took me a while, first of all, to recognize mole and molecules were not the same thing. Because, okay, I'm laughing at my old self. I can now because I understand it. I thought mole was a short form of the word molecule. So when she was saying mole, in my head, I was thinking, oh, she's just trying to use like, kind of like a term of endearment. She's really talking about a molecule, but she's just saying mole, right? Like a short form. Then when she wrote it out, it took me a while to realize that's not what she's saying. Mole is an amount. Molecule is a description of a chemical arrangement, right? Now, as a middle schooler, I'm not able to make that distinction because I was still young in all this chemistry stuff. Anyway, molecules is the term you use for any two or more atoms that come together. Well, the two atoms can be alike, like what we saw right here, right? You have same atoms, or the two atoms can be different atoms. This confused me for the longest time because the teacher kept referring to molecule, but she would switch between the ones that were the same and the ones that were different, but never took the time to explain what this was. And for a long time, I was like, what is she? I don't understand. Is she misapplying the term? And then later on, I understood it. I was like, oh, molecules is just two or more elements attached together. They can be the same, where there'll be molecule of elements, like the one on the left, or they can be different with the molecule of a compound, like the one on the right. Okay? Yeah, chemistry. So, why are we learning about atoms and molecules? Because scientists notice that understanding the atomic and molecular level of matter determines how matter works. It would be like somebody trying to figure out why you do what you do, right? And they say, and you're like, I don't know why I do it. I do it. My mom does it. My grandma did it. And then they say, let's go to your genes. The answer must be in your genes. So these atoms and these molecules will be kind of like genes. This is a very loose correlation, right? When you see the behavior of atoms and molecules, you can extrapolate that to matter in the end. Okay? So we're moving on. We're going to classify matter. When we are studying matter, because we have a lot of matter out there, scientists organize this matter to make it easier for us to study. Right? Just to make it easier for us to study. So classify matter. Matter can be classified according to state. Please notice state and phase are used interchangeably. State is the same thing as phase. We have solid matter, liquid matter, gas matter. So you want to be aware of matter, solid matter, liquid matter, gas matter at 3 different levels. The solid matter shows you the particles in here. These particles are organized very closely together. They're tight. You can see right here, right? They're tightly packed in space. They're so organized. Look at that. Very organized. Organized in space. And then you have liquid matter. In liquid matter, you do have the atoms sort of close together. They're not tightly packed and they're not organized. Okay? So here you have tightly packed, no personal space. The atoms don't really have a lot of personal space. Or I shouldn't call it personal space. Atomic space, that's very small. Over here, you have particles that are very closely packed together, but they're able to move. There is some movement there. And then finally, you have gaseous matter. With gaseous matter, sometimes I'm like, the gases are the introvert particles that kind of like their personal space, right? So yeah, we're around in the same container, but every gas molecule is doing their own thing. They're moving around really fast. They have very little interaction with each other. They're kind of not bothered by the other gas molecules. And so we see what's going on right here. Particles are very widely spaced. Okay? So we classify matter based on the state, physical state, solid, liquid, gas, and then at some point based on the composition, the types of composition that we have in matter. Okay? So we're told here the state of matter changes from solid to liquid to gas when you increase the temperature. From solid to liquid, increase temperature, and you're able to make a solid a liquid. Increase temperature and you're able to make a liquid a gas. Okay. So we're told here that when you're looking at solid matter, the molecules tend to be packed very closely together. Okay. So what I want to do here is, with my non-majors class, we went over the same topic. With them, they had a table. So we went to a table and actually classified the different behaviors. So I want to go ahead and do that here. Oh my goodness. So I'm going to have a table here, and the table is going to look at solid. And with the table, we're going to be looking at space. And then we're going to be looking at volume. And then we're going to be looking at movement. Okay, as we try to classify going from one to another. So let's go ahead and start with solid matter. With solid matter, it says the atoms and molecules are packed very closely, right? So solid atoms packed closely, or I should say tightly, not just closely, tightly, right? So the other thing I want to mention with you guys is also intermolecular force of attraction. Now, we're not talking about this in this chapter, but it does help to explain the behavior of these individual atoms. Something called intermolecular force. So let me actually write this word on the previous page so you can see it. I'll actually abbreviate it here because it's worse to write it like that. I'll call it IMF. This is not the International Monetary Fund. This is the intermolecular space. Intermolecular force of attraction. Intermolecular force of attraction. Oh, sorry. I was supposed to see your question, right? So what's the difference between diatomic atom versus a molecule with the same atoms? Oh, sorry, Victoria. I'm just now seeing your question. When you're saying a molecule with the same atom, can you give me an example? Oh my goodness. Can you give me an example of the molecule with the same atoms? Can you hear me, Victoria? Okay, do you have an example? Okay. Okay, let me see. Let me see if I can. Um, okay, so back to your question, back to this right here, right? I'm glad you asked. So where was I? Let me go back to this page here. Oh my goodness, guys. Okay, so let me expand more on the molecules versus the compound, right? So with the molecules, as far as the picture is concerned, the one on the left is this one here, right? And these are same. Oh, I see what you're saying. The molecule with the same atom is actually diatomic. This is diatomic. Is that what you were asking? You're comparing this to this? Okay, yes. Same atoms is diatomic element. And the one on the right with different atoms, this is a compound. So I thought I did a worksheet with you guys before, right? Where we called this the element and then this the compound, right? So the molecule that has the same elements is the exact same. Well, if there's only two, is the exact same thing as diatomic element because there's some that have four. For example, P4 phosphorus in nature is made up of four atoms like that. And then I don't know if you've heard of sulfur 8. Sulfur 8 is made up of 8 atoms. So you have 1, 2, 3, 4, 5, 6, 7, 8. Now I'm drawing it like this. In reality, it has its own special arrangement, but when you count them, each unit has got 8 sulfur atoms clustered together, and that's how they exist until sulfur is about to react. It's like a support group of single atoms. Okay, and so sulfur does that, phosphorus does that. Now with this one, the ones with a diatomic, the example I think is Brinkelhoff. You know what's messed up? Now I'm kind of getting confused what I've said in what class, so I may say the same thing over again. Just bear with me. Brinkelhoff. So all the diatomics, remember Brinkelhoff, all of these exist as, two atoms together right before they react. While they're single until they react. Right before they react, the two atoms separate and then they're able to react with other elements. Okay? Okay, I see what your question was. Right. So now that we've seen this part right here, atoms are closely packed. With solids, they have a great intermolecular force of attraction. And by the way, this intermolecular force of attraction is the force of attraction that forces that the atoms have for each other that allows for the three physical states to exist. So you can see here, since the atoms are tightly packed, that means they have the greatest intermolecular force of attraction. One solid atom attracts the other solid atom very strongly. Okay? If this is greatest, it affects movement, right? If one atom of a solid wants to move around, it's very difficult. So the best they can do as solids is vibrate in space. They stay in space because they're kind of bound to other atoms, right? Solid, and they just vibrate as though they're cold, shivering. Due to the solids having a high intermolecular force, they're able to have their own volume. They have their own volume and then they have their own shape. So I'll say here volume, yeah. For liquids, I'll say atoms are closed together. They take the volume of container and liquids slide past each other. And then here, intermolecular force, intermediate, in between. With gases, atoms are very far from each other. They also take on the volume. Oh, sorry. Liquids have their own volume, my bad. Liquids have their own volume, but they don't have their own shape. But shape of container. And here, solids have their own volume and then they have their own shape. I didn't have a section for shape. So gases take on the volume of container. So here I say volume and shape of container. Okay, so I was able to fit everything in there. And here they are fast moving and then least intermolecular force. Okay, so I've kind of summarized these behaviors right here. So as you read through all this, you will see examples of solids right here, examples of liquids. And remember, because liquids can slide past each other, it allows them to flow and you can actually pour them out. Okay, and then with gases, you can see that the gases do have a lot of space between them. Because gases have the most space between them, you can actually compress gas. it's not easy to compress a solid. So solids and liquids are not compressible. So you see right here, because gas molecules have a lot of interatomic space, because they're very far from each other, you can apply pressure from the outside like they did right here. They applied weight, which is pressure, forcing the molecules close to each other. You know, if you compress a gas, you end up getting a liquid. If you add so much pressure, right? You end up getting a liquid. Okay, so the next thing we're going to be doing is classifying matter by composition or components. So we're seeing an overview here showing as the macro level. Remember, the macro level is a level that we can see with our naked eyes or even simple instruments like our glasses. And then here we have the particulate level. This is a level to particulate, the level of atoms and molecules, right? So it's showing you pure substance, and then we have compounds and elements. So what I'm going to do here is go straight. I'll come back to this page when we're done to summarize it. So here we're told that matter can be classified as a pure substance or a mixture based on its components. In chemistry, pure just means one type of. So when you see pure, you can just say one type of, and then fill in the blank. It's an atom or molecule or compound, okay? A pure substance is made up of only one component, and the component can be an atom or a compound or whatever it is you're looking at, okay? And its composition is constant. It doesn't change. The difference between a pure substance, anything that is not pure by default is a mixture, okay? And now I look back, I think that we did do the work on determining, okay, so I think I kind of flipped the worksheets because I did the worksheet with you guys where we had to determine the mixture and the pure substance. So yeah, I see that we probably did it too early. We should have done it in chapter 1, not with chapter E. That's okay. You can go back and review that video since we're now covering this to make sure you understood what we're doing in that section, okay? A mixture, by contrast, is a substance composed of two or more components in proportion that can vary from one sample to another, okay? This is just saying a pure substance has one chemical over and over again. So we saw this in our worksheet, right? A pure substance, if the chemical is an individual atom, you have the same atom over and over and over and over again. You can say this is a pure atom, whatever it is, okay? Then let me show you a pure molecule. Pure molecule. Same structure over and over again. Pure molecule. Let me show you a pure compound. Pure compound. I mean, I kind of mix this up. I'm trying to keep it simple, right? Pure compound, pure compound. You just have the same thing over and over and over again, right? Now, when they say that you have a mixture is when you're mixing things up, right? So in a mixture, remember, like we did in the worksheet, you just kind of take, you know, from any one of these, you can mix this and this. You have pure element. And now this is a molecular element. It's still an element because remember, as long as the atoms match, it's still an element. When the atoms are different, and remember at this level, they will show you the difference by making one a different color or a different size. If the elements are different or the atoms are different, then they're communicating compound to you, right? So of course, if you mix these two here, you have mixture of elements. And if you mix these two here, you're going to have mixture of elements. More. Oh my goodness. And compound. This is so loud. Sorry, y'all. Okay, now that we've seen the difference, we can now move on to this part here. I already told you what an element is. I referred to it a lot. An element is a substance that cannot be chemically broken down into a simpler substance. Even when it's diatomic, it's still considered an element because whatever the elements were, when you break it down, they still have the same identity of the element, maybe not the same formula, right? So let me give you guys an example here with the elements. If you have oxygen molecule broken down to oxygen atoms, it's still oxygen before and oxygen after. Okay? So for that reason, this is still an element. On the other hand, with the compound, if you have carbon monoxide and it breaks down, it does produce two different elements. And so this is considered a compound. So compound and then element. Okay? So a compound is a substance composed of two or more elements in fixed definite proportions. Okay? So once we've defined that, now we're looking at mixtures. We've seen the mixtures before. A mixture can be categorized into two types. You have heterogeneous mixtures, you have homogeneous mixtures. Now these definitions are based on our experience. This is based on our experience. Essentially, how we see them. Okay? With a heterogeneous mixture, you can visually see the difference. So heterogeneous mixture, you see the difference. Okay? And then homogeneous mixture, you can't see the difference. Oh my goodness. Okay? You can't see the difference. So for that reason, with homogeneous mixture, you have to rely on experience. Somebody has to tell you there's a difference here. Oh my goodness. Okay. So yeah. Y'all give me just a moment. Okay, I'm back. So with the heterogeneous mixture, we're told here, this is the one where you can visually tell there's a difference. The composition varies from one region to another. So you can have some areas that are more concentrated with one component or the other, or you can have an area where, everything looks more uniform. So the composition doesn't really matter that much. Okay? So give me an example here, and the example we have here is salt and sand mixture. Okay? With salt and sand mixture, no matter how you stir this will always look not uniform. You will always be able to tell where the salt is and the sand is. Even if it's uniform, you still can tell the sand has salt in it, or the salt has sand in it. Okay? So you can tell. Or if you take sand and water. Okay? This will still look heterogeneous. Okay. Now with a homogeneous mixture, once again, experience will tell you there is a difference. Because even though visually you can't tell there's more than one substance, if somebody does tell you, like if you have salt dissolved in water, right? And it's stirred very well to where the salt completely dissolves in the water. You can't tell, right? Visually, you have salt in water. Somebody will have to tell you, hey, there is salt in water. Or if you taste it, you try to drink the water, you realize it's salty water. So in this case here, some kind of experience or somebody has to inform you, will tell you there is a mixture. Or it is a mixture, right? I should say it is a mixture. Okay. So a homogeneous mixture is made up of one or more substances mixed together, but appears to be one substance. Okay? So make sure you know that. Finally, we're moving on to atomic models. So in the atomic models, We're going to talk about the more prominent models that really made a difference. So, in no way am I saying these scientists did not make a difference, but we're not going to be talking about them all the time. Okay. So, this page is more like a FYI. The next page on is the stuff that we have to remember. Okay. So, in the 5th century BCE, Leucippus and his student Democritus were one of the first people to propose that matter around us was made up of small, indestructible particles. So the thing with science is the previous scientists are actually doing the work to help out the new scientists. So even if everything about their finding is not 100% accurate, those who come in behind them are usually trying to perfect or improve their findings. Okay? So Democritus wrote, nothing exists except for atoms and empty space. So he said, when I look around me, the things I can tangibly feel and experience, those are atoms. The things I can't feel or experience, empty space. Everything else is opinion. Okay? But here's the thing that I think is cute or it's kind of funny. He proposed that atoms existed in different shapes. Okay? So imagine if he was right, right? How will we drawing atoms? I always try to imagine. We'll be drawing some atoms as circles. We'll be drawing some atoms as squares. We'll be drawing some atoms as heart. I don't know, as hearts. Oh, I'm doing so bad at hearts, but you know what I mean, right? We'll be drawing different shapes atoms if he was right, but he wasn't right. So at least all we have to do is draw circles, right? But his idea was things are a different shape in life because the atoms are shaped differently versus all atoms are round, but things are differently shaped because of the way the atoms are arranged. He said no, they have different shapes. So that was a I think that's interesting. Hey, anyway. So years later, Plato and Aristotle did not embrace the atomic ideas of Leucippus and Democritus. They actually said matter has no small parts. They said everything around us is made up of various proportions, different compositions of fire, air, earth, and water. This kind of sounds like a musical group or something, like a band, fire, earth, air, and water, right? So everything we see around us, the table I'm standing in front of right now as I teach you guys, is made up of fire, air, earth, and water, different compositions of it. Okay. Then years later, we have an English chemist named John Dalton. So here's where we start to actually be accountable for this scientist. He offered a convincing evidence that supported his early atomic ideas, right? Okay, so not only his ideas, but he also went back to what Leucippus and Democritus was saying. So he said, you know what? Leucippus and Democritus were onto something when they said matter is made up of atoms. Maybe not differently shaped atoms, but atoms. So his is called the modern atomic theory. Okay. Now, in the world of chemistry, the 17 and 1800s is modern. Well, we still call it that because it was much newer than the other ones. Okay. So his modern atomic theory and its laws eventually, whatever Dalton came up with, eventually led to conservation of mass, a new law that came up after Dalton, the law of definite proportions, and the law of multiple proportions. So these are actually labeled as Dalton's success. So not only did he come up with his own laws, he inspired other laws that came up later. After people understood his laws, they came up with these laws. Okay? So let's see what Dalton said. John Dalton and his atomic theory. John says, well, we'll call him Dalton, his atomic theory. He said elements, each element is composed of tiny, indestructible particles called atoms. Okay. So I when I read stuff, I try to be engaged in what I'm reading. So if I can't really do much with it, if there's a picture I can draw, I try to draw a picture. So let's look at sodium. Let's say sodium element is made up of sodium atom. So this would be sodium atom. Okay? So within the element, we essentially have sodium atom. Okay. All atoms of the, by the way, the atoms are round, just in case it wasn't specified here. Dalton said all atoms are round. They don't have different shapes. He says all atoms of a given element have the same mass and other properties that distinguish them from atoms of other elements. So what he's trying to say here is, if you look at sodium atoms, these are sodium atoms. They're usually solid, okay? Sodium atoms. And compare them with lithium atoms. I'll make lithium smaller. You can tell sodium atoms are different from lithium atoms because all the sodium atoms are like each other, but different from the lithium atoms. Okay? Sodium atoms behave like each other, but they behave differently from lithium atoms. So they have these properties that makes you go, oh, no, no, this is not a sodium atom. This is actually a lithium atom because it doesn't behave like other sodium atoms. Okay? So we're moving on. We're done with these two. Number 3, atoms combine in simple whole number ratios to form compounds. What do you think he's saying? Okay, he's saying when atoms combine to form compounds, when they come together to form compounds, they combine in simple whole number ratios. Okay? So let's say atom, sodium, is trying to combine with chlorine. Okay? One sodium combines with one chlorine and they form sodium chloride. We never have half a chlorine and a whole sodium. This is possible, but this is not possible. We never have half atoms combined. Atoms don't break up and combine in halves. Okay? They combine in the whole number ratios. Okay? Then number 4, atoms of one element cannot change into atoms of another element in a chemical reaction. So the context here is, as long as the reaction is chemical, one atom cannot magically become another. So you cannot start with, let's say, hydrogen, and then it breaks down to oxygen. This is not possible, okay? So you can't go from one starting material and then magically get another in a chemical reaction. So the way we see different results, or the way we have the products looking different from the reactants, the atoms just change the way they're bound together, or they change their positions. So in a chemical reaction, atoms change positions. Okay? Atoms change positions. So here, this is the end of Dalton's atomic theory. So remember I told you the success is, once the theory came out, it's very popular. There's some people out there who are questioning the theory. Others out there are trying to take the theory to discover other things, right? The law of conservation of mass. I think Dalton actually put this one together. The context here, context is chemical reaction. So this law is only seen when you're looking at a chemical reaction. And what they say is, in a chemical reaction, matter is neither created nor destroyed. That means the mass of reactants equal mass of product. Okay? So in this section here, the kind of questions they could ask you actually is written right here. They could give you the mass of both reactants. Like right here, we have a specific mass of sodium, specific mass of chlorine, and these are being added in the reactants. So your product has to have the same mass for the law to be true, for the law to work. Okay? Because mass of reactants equal mass of product. context of this law, where we see this law works, is in a chemical reaction. Okay? So then we move on and we see the other law that came up to support Dalton's law. Scientist Joseph Proulx made observations of the compositions of compounds. So Joseph Proulx essentially said, when you look at chemical compounds, if you look at water, for example, regardless of where you get the water always has two hydrogens for every one oxygen. Okay? So we're told here, the law of definite proportions, the context here is chemical compound. Okay? Later on in my journey in chemistry, I learned that the context was so important in the definition. So we're told here, all samples of a given compound, example, our water, regardless of their source, you can have what is called tap water, pure water or purified water, or spring water. Okay, so you can have all those waters or how they were prepared. Water from the lab have the same proportion of their constituent elements. Now, somewhere here is supposed to say by mass. Okay, so all they're saying here, regardless of the source of the water, it will have two hydrogens and one oxygen. Okay, they will have the same consistent composition. If you flip the oxygen and say you have two hydrogens and two oxygen, this is now peroxide, hydrogen peroxide. It's not water anymore. It looks like water, it pours like water, the color looks like water, but you try to drink that liquid and it will burn you. So you know very quickly it's not water. It became not water once you changed the ratio of oxygen, when you added two oxygens to two hydrogen. Okay? So, since we're comparing mass, right? The ratio is by mass. We'll come out with a unit called a mass ratio. So the mass ratio is the ratio used to identify compounds based on the ratio of the elements. Okay? Later on, it's used to identify compounds. When you're trying to figure out what is this compound, somebody's arguing with you about the compound. You can say, listen, I don't have to argue with you. The mass ratio based on the components proves it's one chemical versus the other, one compound versus the other. Since I use water as the example here, you can use the masses of oxygen and hydrogen in water to figure out the mass ratio of water. They did it here, okay? I'll do it too. I know water has two hydrogens for every one oxygen, right? The two hydrogens weigh 2 times 1 gram. By the way, the one here is from the periodic table. I don't have it with me, but I just have it, the numbers memorized. So hydrogen, each hydrogen is about 1 gram, okay, per mole. And then we have two of them, so it's going to be 2 grams. And then we have one oxygen. Each oxygen is about one oxygen, about 16 grams per mole. It's like 15.999 per mole. Okay? So you see how they worked it out here. The mass ratio, here's the general formula, is equal to heavier atom mass divided by lighter atom mass. And then we use this ratio as a fingerprint to identify or to prove the identity of the compound. Okay? Once again, it's all about the identity of compound. What is this? Because you know, chemistry is the mystery of the chemicals. So if you're doing a mystery, if you like watching mysteries, oh, I love watching mystery movies, right? Chemistry, mystery, who done it, who is it, right? You have to identify the element. or the compound that you're working with. So in this context here, we're looking at the compound. Take the heavier atom mass and the lighter atom mass and then divide them. So the heavier of the two here is 16 gram per mole, divide by 2 gram per mole, and we end up with 8, or 8 over 1. So you can use this as 8.0 or 8 over 1. So then you can conclude, you can walk away from this saying H2O has 8 grams of oxygen for every 1 gram of hydrogen. That's the conclusion we're making with all of these numbers. So if you have a compound that looks like water, smells like water, pours like water, you're trying to figure out, is it water? Figure out the mass of oxygen. Compare it to the mass of hydrogen. If you get 8 grams of oxygen for every 1 gram of hydrogen, guess what it is? It's water. Okay? Yeah, it's water. Sorry. I'm talking, I had to put earplugs because it got so loud, so I don't know if my voice was different, but anyways. So yeah. So improving the law of definite proportion. Let me do this last part here, and then it will allow us to be able to work on the law of multiple proportions next week. So right here, we're trying to prove this law of definite proportion. We're told we have 2 samples of carbon dioxide decomposed into their constituent elements. One sample produces 25.6. So we have 2 samples of carbon dioxide. Okay. One sample has got oxygen and then carbon. 25.6 grams of oxygen, 9.6 grams of carbon. The other sample has 21.6 grams of oxygen and then 8.1 grams of carbon. Show that these results are consistent with the law of definite proportion. So what I want to do is we're trying to find the ratio, right? And then we're trying to find, is that ratio proving that this is carbon dioxide? Well, these are based on experimental results. So what I want to do is go outside the experiment and find out, what should the mass ratio of carbon dioxide be? So what's the actual mass ratio? So what I'm going to do here is use, even though they gave me these numbers here, let me use periodic table masses, right? In carbon dioxide, let me actually get a brand new page down here because that will help. In carbon dioxide, so in CO2, I actually have 1 carbon. So the carbon mass is, we have 1 carbon, the carbon is 12 grams per mole. And then we have oxygen, there's 2 of them, and it's 16 grams per mole. Okay, so oxygen is 12 grams per mole. This is what, 32 grams per mole. So using, what I'm doing right now, once again, I'm using periodic table to, I should have written this somewhere else. Hold on. Let me write this right here. So this is CO2, right? I'm using periodic table to determine mass ratio of carbon dioxide. Okay, because once I get my number, I can compare it with what these experimental results were. How do I judge my experiment is true? By judging my experiment data with the other experiment data. I have to use something outside, right? So I'm going to use periodic table as the standard. Okay, if it's true in the periodic table, it has to work with the results. Anyway, of the 2, this is larger and this is smaller. Okay. So oxygen over carbon is going to be 32 grams per mole over 12 grams per mole. Divide here. Okay. Okay, 32 divided by 12. What do I have? 2.6666, 2.67. Okay. My ratio is 2.67 or 2.67 over 1. So as long as I have 2.67 grams of oxygen per 1 gram of carbon, I have carbon dioxide. So this is the ratio I'm looking for. This is proof that it is carbon dioxide, okay? when you take the mass of carbon, I mean, sorry, mass of oxygen over mass of carbon. Okay, let's go back here and see the masses we got. I'm going to do the same. I'll take the mass of oxygen divided by mass of carbon for this 2 and see what I get. Okay, can I make this a little bit smaller? Yeah, they're right over there. So mass of oxygen over mass of carbon. Okay, top one, 25.6 grams divided by 9.6 grams. Bottom one, 21.6 grams divided by 8.1 grams. Let's see what we get. That's the last thing I'll work on and I'll let you guys go. Last thing, 25.6 divided by 9.6, 2.67. Look at that. 2.67. This is definitely CO2. Yeah. Bottom one, 21.6 divided by 8.1. 2.67. Okay. Therefore, CO2. Okay. I had to figure out my own standard. Well, how do I know my experimental results are correct? You never judge your experimental results by other experimental results. You have to use an outside standard. So I use the periodic table to figure out what should it be. And it said right here, when you divide the two numbers, you should get 2.67. If you do, that will be proof it's CO2. Well, I got it twice, so my data was correct. I can say, according to the law of definite proportion, this is definitely, I want to use that word again, CO2, right? So what I'll do is next time we will start here. I'll write myself a note, start here. Does anybody have any questions? We are done for today and the noise has stopped for a little while. Oh no, well, sorry, my bad. Since they worked it out, we don't have to start here. We can go beyond to here. This is going to be start here. When we meet next time, next week, we'll start right here, okay? If we get a little bit ahead, don't worry about it. Just go ahead and work on the stuff. You know, if you are not able to keep up with this pace, I mean, the videos are recorded. I make sure they are recorded, so you can go ahead and go with that. But we are close to, we're not halfway yet, but we're kind of close to halfway. Okay, I want to make sure when it comes to the math, we have a lot more time with the math and the problems. And we'll need extra time with chapter 2 anyways, because that's quantum. Okay, when we get to it, you understand. We'll need extra time there. This is all I have for today, guys. So hopefully the recording went well, even though there was all that noise in the background. Hopefully it went well. Do you guys have any questions? Any comments? Okay. If not, this is all I have for today. Thank you very much. I'll see you guys on Monday. If you're working on problems in the homework and you have questions, you can feel free to email me. Other than that, I'll see you guys on Monday. Okay.